Okay guys, so this is the first video in a series on physical chemistry. So the first thing that we're going to talk about is just a few preliminary ideas. Really, it's just an introduction to the course, and then some basic definitions that I wanted to go over that will be helpful to us as we start getting into the meat of the course. So this is just a few slides introducing physical chemistry as a subject. I'm sure you'll find many definitions if you start searching around for them. I typically think of physical chemistry as a branch of chemistry that uses mathematics and physics and has a focus on the structure and properties of matter, as opposed to, say, for example, synthesis and the details of chemical reactions that can occur. In physical chemistry, we tend to focus much more so on structure and properties, as well as behavior in some of the sub-branches. There are different sub-branches of physical chemistry. One of them, chemical thermodynamics, will be the sub-branch that we study first. It is based on a larger subject, thermodynamics itself, which is really in the domain of physics, but then chemical thermodynamics is the application of that branch of physics to problems involving chemistry. In particular, we'll review important ideas from thermodynamics, and then we'll apply those to topics in thermochemistry, and especially the topic of calorimetry, which refers to the techniques that are used to measure heat. We'll also apply chemical thermodynamics to phase transitions, to mixtures, focusing mostly on liquid solutions. We'll look at the thermodynamics of chemical reactions and how that relates to chemical equilibrium. A smaller subset of notes, which will probably be de-emphasized as far as the course assessments go, relates to electrochemistry, but you can also lump electrochemistry in with physical chemistry, although much of it in modern practice you might consider to be analytical chemistry. Nevertheless, there's a close tie with chemical thermodynamics, of course. Another sub-branch of physical chemistry that we're going to look at will involve the kinetic theory of gases, as well as some transport properties of matter. So the kinetic theory provides us with a very simple model for understanding gases and their properties. As far as transport properties go, we talk typically about things like diffusion of a gas or diffusion within a liquid, viscosity, properties of liquids, and then for electrolyte solutions, we also you can study that from a transport theory perspective using the same techniques to study electric or ionic conductivity, and the same techniques apply to thermal conductivity as well. So there's quite a few applications within the transport theory section. A very important branch that we'll dedicate some time to is the study of chemical kinetics, which involves formulating the rate laws and reaction mechanisms for various chemical reactions. We will focus on some of the fundamental ideas, as well as some more in-depth examples. And then behind that is our different ways of understanding chemical kinetics. So transition state theory is a very important, has a number of very important concepts that we'll go through. And then the more modern approach, or the modern research in chemical kinetics, focuses to some extent on chemical reaction dynamics. In the not too distant past, a lot of research effort went into and still goes into understanding the reaction dynamics of gas phase reactions, although more and more the field is turning to reactions taking place in the condensed phase, so in the liquid state, typically. Those cover the main topics that we'll do in this course. As you probably know, physical chemistry is usually taught or is often taught as a 2-semester sequence, and so in the second semester, you would study things like quantum chemistry, where you're reviewing atomic and molecular structure and then going into much more detail. Things like intermolecular interactions would fall in the domain of quantum chemistry. And then one of the main applications of quantum chemistry is towards understanding spectroscopy. As you know, spectroscopy is a major tool in chemistry, and so all sorts of different types of spectroscopy would be studied in that second semester, in particular microwave spectroscopy, infrared, UV vis, to some extent X-ray spectroscopy. NMR, of course, as we know from our studies of organic chemistry, is hugely important. And then related to NMR are some similar types of techniques involving electron resonance. And so you see in parentheses are the different types of molecular processes that can be interrogated using these different spectroscopic techniques. And so really the aim of that second semester course is to get us in position to being able to understand spectroscopy and how to interpret spectroscopic signals. Not so much from an analytical chemistry perspective, but just in terms of the nuts and bolts of how does the spectroscopic technique work. Finally, in the second semester, there's usually a brief, a few weeks maybe, dedicated to statistical mechanics, which is it's a mathematical approach that bridges microscopic and macroscopic thinking. So it bridges the world of atoms and molecules, which is described by quantum mechanics, to the world of thermodynamics, which involves macroscopic amounts of matter. And so there's a number of, as the name implies, statistical mechanics. There's a number of mathematical methods that are used in that theory that are introduced in the second semester course. Topics that are important in physical chemistry that often don't get taught, usually just due to time constraints, will involve a more detailed study of materials and characterization of materials as well as their properties, macromolecules, which are usually discussed in biochemistry courses, but then there's also supramolecular aggregates, solid state chemistry, as well as surface chemistry, and techniques like crystallography. They just often don't make it into the normal course sequence. Nevertheless, they are very active areas of research and important to be aware of at the very least. So that was my introduction to the topics that are covered. If you find yourself getting very interested in physical chemistry, I wanted to give you a list here of the most important, or at least very often cited journals in physical chemistry. So a number of these, the first several, they come to us from the American Chemical Society. So the Journal of Physical Chemistry, parts A, B, and C. These are dedicated to the different topics that you see here. The Journal of Physical Chemistry Letters is meant for high-impact research that would be of interest to a broad audience in the form of short articles. So as soon as the work is ready, it can be published very quickly in the Journal of Physical Chemistry Letters. A review of physical chemistry, the annual review of physical chemistry, has much longer articles which have extensive reference sections that you can use to really find out how do I dive into a particular topic within physical chemistry. If you can find an article on that topic in the annual review, then it's usually a very good introduction to a subject that's actively being researched. Faraday Discussions is a nice journal that it often has issues that are dedicated to specialty topics. So you might find that in a particular issue of Faraday Discussions that the entire issue contains multiple articles that will be of great interest to you if that issue happens to be dedicated to that particular topic. On this next slide, I just listed a number of other journals. We do have access to the Journal of Chemical Physics at our campus. These other ones, I don't think that we have access to them, although you can typically get any article that you want through interlibrary loan. And they usually have a 24-hour turnaround period. You just have to go through the librarian in order to get those articles. I know that many of you are interested in organic chemistry, and so there is a Journal of Physical Organic Chemistry if that's what you're interested in. If you're in education, or if you just want some articles that are written towards topics related to undergraduate level physical chemistry, the Journal of Chemical Education has a number of articles on all sorts of topics. Many of the laboratory experiments that we do in physical chemistry and probably several of the other lab courses in the undergraduate curriculum, they are based upon experiments published in the Journal of Chemical Education. And so this is a great resource just to know about. And this one is also an ACS journal, so we do have access to this one from within our library system. Well, next what I wanted to turn to was an introduction to some concepts in thermodynamics. So the first topic that we are going to study is thermodynamics. So the next few slides just are going to go over some basic definitions, nothing difficult to comprehend. After that, we'll start our study of gases, and then we're going to go back to thermodynamics in a lot of detail. And so here, I just wanted to identify some of the lingo that we use when we're talking about thermodynamic systems. So first of all, one thing to appreciate is that thermodynamics is used to describe matter at the macroscopic scale. So when you're talking about a thermodynamic system, you're not directly talking about the molecular structure, what the individual molecules might be doing. Thermodynamics deals with the human scale and above. We're talking about macroscopic quantities of matter. The term system refers to a portion of the universe that you are interested in studying. If you don't care to be so grand as to think about the whole universe, you can just talk about the total system, and you're interested in a part of that total system, which we call the system. The term surroundings refers to everything else that is not the system. And then it's important to think about what kind of boundary that you have between your system and surroundings. So I'm just going to switch over to my camera here and just draw a very simple diagram that's often used to introduce these topics. It's sort of a Venn diagram here. Here we have the universe. Here's our system. Everything else is the surroundings. Okay? And the system and surroundings may or may not be interacting with one another. It depends upon the nature of the boundary between them. And that boundary is quite important, okay, because it's going to dictate what types of processes that system can undergo. Okay, so this is the basic concept of a thermodynamic problem. You have a system, you have the surroundings, and you have the boundary between them. Now, in thermodynamics, what we're interested in doing is characterizing the so-called state of the system. Okay? And in thermodynamics, the state of the system is defined in terms of its macroscopic properties, or you could call them variables. Okay, so these are quantities such as pressure, volume, number of moles, temperature. The values of these quantities define the state of the system. And when the system undergoes a change from one state to another, these quantities or variables can change. There are four main concepts in thermodynamics, and we're going to study all of them here in the first portion of the course. The first big concept is the idea of equilibrium. And the term equilibrium refers to a type of state that has uniform and constant in time properties. By uniform, think about the pressure of a gaseous system. A gas at equilibrium will have a uniform pressure throughout the entire spatial domain of the system. It will have a unique and well-defined temperature. Right? In one part of the system, the temperature is the same as the temperature in every other part of the system. That's what I mean by uniform. Constant in time, the temperature can't be changing. If the system's temperature is changing, then that system is not at equilibrium. So that's what equilibrium means. It's a state with uniform and constant, unchanging properties. The next big concept in thermodynamics that we want to think about is the energy of our system. So energy is another property of the system. Okay, so we can think of the system as possessing energy. And what energy is a measure of, from physics, the definition is that it's the capacity of a system to perform work. I like to add on to that, to perform work or to do heat. And we'll talk about heating problems later on in the course. So energy is a big idea in thermodynamics. The next concept is somewhat harder to explain. It's called entropy. Okay? Entropy is another property of the system. And so from a thermodynamics perspective, the system possesses an amount of entropy. What does entropy represent? Well, there's different ways of describing it. The way that we're going to follow in this course involves the information theory definition of entropy, where we can think about the entropy as an amount of information, molecular level information, that a macroscopic observer does not know about the system. Okay? Now we're going to spend quite a bit of time unpacking that later on in the course, but for right now you can just think of entropy. It's a property of the system, and it represents what a human observer does not know about what the molecules of the system are doing. The last big concept in thermodynamics is called free energy, and it refers to the amount of energy that the system possesses that is actually available to perform useful work. Okay, so you can think of the energy of a system, that some of the energy that the system has can be used to do work, and then the rest of that energy is not available to do useful work. And so the part that can be used to do work is called the free energy. Okay, so these are the big ideas in thermodynamics, and we'll be talking more about each of them in detail as we go. There are also 4 laws of thermodynamics. So along with the 4 concepts, we have 4 laws. The Zeroth Law defines equilibrium, much like we've already done. I'll talk about it in a little bit more detail within this set of lectures, this set of lecture slides. The first law deals with energy. It's a bookkeeping tool that allows us to keep track of the system's energy and the surroundings' energy. It's also known as the law of conservation of energy. The second law and the third law both deal with entropy. The second law uses entropy as a tool to distinguish between processes that can occur and processes that cannot occur. Okay, so it allows us to distinguish possible from impossible processes that our thermodynamic system can undergo. The third law is useful. It's particularly useful in thermochemistry applications. It defines a scale, essentially, for calculating entropy. And so we'll make use of that in our entropy calculations. Okay? We'll get to all of these things later. I think in just a moment or so, I have a couple of slides on the Zeroth Law. Before we get to that, I wanted to go over another concept. It's very useful to express this concept now before we get into any of the details of things. So what this slide is meant to do is to convey the difference between a macroscopic state in thermodynamics versus a microscopic state. So in order to specify the thermodynamic state of a pure substance, you need to specify 4 quantities. Okay, so there's 4 variables that you need to specify the thermodynamic state of a pure substance. These are the pressure, the volume, the number of moles of that substance, and the temperature of that system. If you know those 4 things, then from a thermodynamic perspective, you know everything that you need to know. Right? What that means is that from the thermodynamics perspective, knowing the 4 quantities is a macroscopically complete set of variables. From those 4, everything else can be determined. So that's true from the macroscopic perspective, but from the microscopic perspective, that's obviously not correct. In fact, you would need a great many number of variables in order to specify the total molecular state of a bulk system. At the very least, you would need to know the position and velocity of every single molecule. In addition to that, because molecules have an internal structure, you would need to know information related to that. And that's just for one molecule. Right? So you would need at least 6, if not more, variables. You would need to know at least 6 values in order to define the state of a single molecule. For a bulk system where you have on the order of 10 to the 23 molecules, you would need 6 times that many pieces of information in order to identify explicitly the total molecular state of the bulk system. Okay, obviously that's impossible. So from the perspective of thermodynamics, knowing only 4 variables is incomplete. You have incomplete information about the system at the microscopic level. But from the macroscopic perspective, knowing the 4 variables is all you need to know. And so this figure here, which I've taken from our supplemental text, Poirier, A Conceptual Guide to Thermodynamics, this figure here encapsulates that difference between the macroscopic state and the microscopic state. So on the left, we have the thermodynamic picture of our system. Here we've reduced it down to 2 variables, which is just fine. You could imagine that there would be another dimension representing pressure and another dimension representing number of moles, but you get the idea that a single thermodynamic state is described by a point in this temperature volume space. Well, it turns out that there are very many microscopic states corresponding to that single macroscopic state. Right? You can think about it like this. The molecules of a gas are in constant motion, right? So their positions and their speeds are changing all the time. Yet the temperature and volume and pressure and number of moles of the gas inside the system is fixed right? So the macroscopic variables are fixed, even though the microscopic variables are constantly changing. So to each single thermodynamic state, there correspond many possible microscopic states. And this is what is meant by this one-to-many relationship between thermodynamic states and microscopic states. Okay? This idea of having many possible microscopic states is central to the idea of entropy, at least when you're using the information theory approach. Okay? And so that's why I wanted to sort of establish this idea now, and then we'll come back to it as we discuss entropy in more detail later on in the course. You only need 4 variables to represent a macroscopic state. You need a huge number of variables to represent a microscopic state. So this is information coming from the prologue of the textbook. We are going to present one concept from statistical thermodynamics now because it is frequently used in order to explain other concepts in physical chemistry. Okay? And this involves what's called the Boltzmann factor. So the subject of statistical thermodynamics relates microscopic states to macroscopic states by counting them up. In fact, that's what statistics is all about. It's about smart ways of counting things. Okay? And you need to be smart about how you count up a system that involves on the order of 10 to the 23 objects, right? You can't count them individually. You have to use mathematical techniques to do it. And so that's what statistical thermodynamics is all about, essentially. But in the end, you're just calculating weighted averages. Okay? So for example, the thermodynamic energy, which we are representing by the symbol U here, is a weighted sum over all allowed microscopic energy states. Okay? So when you report the energy of a system, or when you're doing a calculation of the energy, you can think of it from the microscopic perspective as what I'm going to do is I'm going to take all of the allowed microscopic energy states, and then I'm going to take an average of them. And so this is what that average looks like. It's a sum over the number of states. You have the energy of each state, and then this is the weighting factor, this exponential, which is called the Boltzmann factor, divided by Q, which is called the partition function. This is the probability of encountering that particular state. Okay, so you have the energy weighted by its probability. And the form of the partition function is given by a sum over all of these exponentials. As I was saying before, the exponential factor here, this exponential Boltzmann factor is what it's called, it represents the population of molecules that have that particular state. It's a weighting factor. Okay? So e to the minus the energy of that state divided by the quantity k times t, where k is called the Boltzmann constant, and T would be the temperature in Kelvin. So we have an energy for a particular state I divided by kT. We take the exponential of the negative of that quantity, and then we divide by the sum of all of those weighting factors. Okay? And it gives us a fraction. What's the fraction of molecules that have energy EI? And so if you take that fraction of molecules that have energy EI and multiply it by the energy EI, and then add that up over all possible states I, that's going to give you the weighted average. It's going to give you the average thermodynamic energy. We will use the Boltzmann distribution at different points throughout both this course and the next physical chemistry course. Well, the next couple of slides here are meant to elaborate upon the Zeroth Law of thermodynamics, which deals with equilibrium. So as I mentioned before, Equilibrium is a state of the system. It's a category of states. That is, all equilibrium states have these characteristics. That is, that the variables are uniform throughout space and they don't change with time. Okay, so an equilibrium thermodynamic state, you can think of it as basically standing still. Okay, it's not changing, and all of the properties are constant throughout. Now that does not mean that the molecular state, the microscopic state, is not changing. In fact, it is, right? So even though your macroscopic variables, pressure, volume, number of moles, and temperature, even though those are constant, microscopically the molecules are bouncing all around. And so we refer to this as a dynamic equilibrium. Macroscopically things are fixed, but microscopically the molecules are moving all around, and the molecular state, the precise molecular state, is changing. Sometimes the term thermal equilibrium is used to refer simply to equilibrium with respect to temperature. That is, only the temperature is constant throughout, only the temperature is fixed with time. And likewise, the term thermodynamic equilibrium means that all of the variables are in equilibrium. So the idea here being, you may have equilibrium with respect to temperature between the system and surroundings, but for example, the pressures might not be in equilibrium, or the volume, or the number of moles, or something like that. Okay, so thermal equilibrium refers to just temperature. Thermodynamic equilibrium refers to all thermodynamic variables. This slide introduces us to the idea of an equation of state. So every pure substance has a so-called equation of state that determines which states are in thermodynamic equilibrium. Okay, so we can represent that equation generically in this fashion. You have some function of the thermodynamic variables, so pressure, volume, number of moles, and temperature. There's some function relating these variables together, and we just set it equal to 0. Okay, whatever this is, whatever this function is, it is only satisfied by states that are in equilibrium. That is, only certain combinations of pressure, volume, number of moles, and temperature will satisfy this equation of state. All other combinations of pressure, volume, number of moles, and temperature do not satisfy the equation of state and therefore are not equilibrium states. Given that we have 4 variables and the equation, it means that there are really only 3 independent variables, right? I may be able to specify pressure, volume, and number of moles, but I haven't yet specified the temperature, but really I don't need to, because I can determine the temperature from the equation and the fact that I know the other 3 variables, right? So given any 3 of the variables and the equation of state, you can always find the 4th variable. Oftentimes, the number of moles within our system is fixed. And so really, if number of moles is fixed, then there's typically only going to be 2 independent variables, right? If number of moles is already fixed, and we know pressure and volume, then we can determine the temperature. Okay, so typically, we'll have only 2 independent variables that we need to worry about. It's also important to realize that none of these variables are inherently special. Okay, we can choose any 2 variables that we want. Like, let's just assume number of moles is fixed. We will typically need to what we'll typically do is choose 2 of the variables to be the independent variables, and then the other one will be the dependent variable. And what I wanted to point out here is that we are free to make that choice as we see fit. That is, we can choose the independent variables as we want to suit the special needs of our problem. And you typically do that to make the problem as easy as possible in order to solve it. So here is an example from Poyer's book describing a very simple equation of state. So this is the pizza system equation of state. And the idea is that you have three friends. You've got Paul, Valerie, and Thomas. And they are each sharing a pizza that has 8 slices. And the presumption is that they're going to eat all 8 of them. And so the number of slices that Paul eats, P, plus the number of slices that Valerie eats, V, plus the number of slices of pizza that Tom eats, T, must equal 8, the total number of slices of pizza. So this represents an equation of state. Paul might eat all 8 pieces, which would leave none for Valerie and Tom. And so that would give us this point right here. Or Valerie might eat all 8 pieces, in which case Tom would have 0 and Paul would have none. And the same thing for Tom. And then any combination of distributions of pizza slices that fits on this triangle here satisfies this equation of state. Okay, so the variables that define equilibrium, or the values for equilibrium states, they all satisfy the same equation of state. We're going to find that material systems do the same thing, right? Instead, we're going to have pressure, volume, and temperature, and then we'll start with gases. For gases, the ideal gases, we'll find that the equation of state looks like this, the ideal gas law. And so this is the equation of state for gases that behave ideally. It relates the pressure, volume, and temperature of the gas for equilibrium states. I wanted to say just a word about non-equilibrium. So systems can find themselves in non-equilibrium state. It's not that they don't exist. It's just that they don't it's just that the values of pressure, volume, number of moles, and temperature do not satisfy the equation of state for non-equilibrium states, or they're not well defined in the sense that the temperature may be changing, or the temperature may not be uniform throughout the system that you're talking about. If that's the case, then the equation of state doesn't work anymore. You have a non-equilibrium system, and that non-equilibrium state is going to, at some point, spontaneously change into a new equilibrium state. Okay, so non-equilibrium states are not thermodynamically stable. They will, at some point, eventually reach a new equilibrium. It may take forever for that to occur, but it will happen eventually. Here I have a comment. This is actually a story. It's meant to refer to a diagram that I'm supposed to draw. So I'm going to go back to the paper. And so what we're talking about in this second bullet point is a thermodynamic system that looks like this, where you have really 2 subsystems that are about the same size. And what you're going to do is bring them into contact with one another. And so it may be useful to think about temperature in this case. So suppose that we've got these objects here, and they are at, let's suppose that they're at the same temperature. And so if you bring them together to form a thermal contact between them, what you'll find is that the temperature does not change, because the temperature of the 2 subsystems are in equilibrium already. If they were at different temperatures, what would happen when you brought them together into thermal contact is that you would find that the temperature of the hot object would start to decrease and the temperature of the colder object would start to increase, until eventually the 2 subsystems' temperatures were identical. And then we would say that the system has reached equilibrium. So now we're ready for the Zeroth Law of thermodynamics. We've sort of introduced the idea of equilibrium states. And the Zeroth Law, it's written rather axiomatically. It reads more like a math statement than anything else. If two systems A and B are in equilibrium with the third system C, then systems A and B are also in thermal equilibrium with one another. And I'm going to go back and draw another picture here. This is often represented by a diagram that looks like this. So let's suppose that we've got our systems A and B here, and here's our system C. What the Zeroth Law is saying, if A and C are in thermal equilibrium, that is, if they have the same temperature, and B and C are in thermal equilibrium with each other, they have the same temperature, then we know A and B must also have the same temperature. Okay, and so this is a definition of how thermal equilibrium works. What it does is it establishes thermal equilibrium mathematically as a so-called equivalence relationship, and it effectively provides an empirical definition for temperature. That is, the temperature of an object is the variable that you use to determine whether or not it is in thermal equilibrium. Likewise, you can use the idea of thermal equilibrium to define the temperature of an object. In any case, this provides the basis of how thermometry works. So if you pretend that object C here is your thermometer, and you go and you measure the temperature of a glass of water, and you establish it to have a temperature of 25 degrees Celsius, and then you take your thermometer and walk across the room and measure the temperature of a second glass of water, and it's also at 25 degrees Celsius, then you know that if you brought the two glasses of water together, they would already be in thermal equilibrium. So that's the Zeroth Law. This idea of contact, thermal contact between two subsystems. There are different ways in which thermodynamic systems can be brought into contact, and each of these different ways is associated with different pairs of variables. And they also correspond to a different type of energy transfer. What we've discussed so far has been thermal contact. That is, you have a system and its surroundings, and then if there is thermal contact between the system and its surroundings, you would classify the walls that separate the system from the surroundings as being diathermal. That is, the walls will allow heat to be transferred. Contrast that against adiabatic walls. Adiabatic walls prevent heat from being transferred. We associate thermal contact with the variable temperature and the quantity called entropy. And we'll discuss this in more detail later as we introduce entropy specifically. Another type of contact between a system and its surroundings is mechanical contact. And mechanical contact involves typically a movable wall. Okay, so a wall that, basically think of it like a balloon that can expand or be compressed. Okay, that's what I mean by a movable wall. Or something like a piston, where the wall can be pushed in or pulled out. For movable walls, there is mechanical contact, and that allows energy to be transferred through the process of work. And the variables that we're going to focus on for mechanical work will be those of pressure and volume. Now, there are other ways to perform work, but the ones that we're going to focus on in physical chemistry involve what we call pressure volume work, where a gas expands or is compressed. Another type of contact that we'll discuss much later in the course involves diffusive contact or chemical contact between the system and surroundings. And so this is where you have either a permeable wall or a non-permeable wall. The permeable wall allows matter to flow freely between the system and surroundings. The non-permeable wall does not allow matter to flow. So that will involve the number of moles of a component in your system. It's also going to involve something called the chemical potential of the system, which we'll introduce later. And then the product of number of moles and chemical potential has units of energy. Just like heat and work have units of energy, this product also has units of energy. So we were going to discuss, we'll discuss each of these contacts in more detail as we go throughout the course, as we describe thermodynamics. So I'm going to go ahead and stop this video here, and we're going to pick up the topic of gases in the next video.